It's a real pleasure to be here and to be invited to speak. It's my second, thank you. It's my second year. What I'll try to do is describe how we work and what our approach is for providing imagery and data to practical farmers. As an introduction, my role is to provide solutions to farmers. And I completely agree with the approach that other people have described. But my talk, and if I had slides, it would be much clearer. I would be able to show you the pictures and how we supply data from our research to growers. One of the most important things is that each data set that we have has to solve some kind of problem. So if there is I work on diseases of plants. If there's a problem with the disease, a grower may have a solution to that disease, or we may have developed a solution to the disease. But how do we use remote sensing and drones and UAS to transfer better data so that they can more accurately control the problem? So, one of the big stumbling blocks that people have is how do they take, if you're losing a certain amount of money to a disease, how do you calculate that amount of money can be used to help solve the problem and still make more money? So it has to work economically. And that's one of the challenges that we have, is that we're no longer working with simply toys of technology, but we're applying those toys to solve the problem. 10 minutes seems a lot longer when you don't have slides. That's okay. So one of the diseases that I work with is one called fairy ring. And it's a disease of cranberry that is a perennial crop. And as that crop develops over 100 years between plantings, the disease will come in and start to shorten the life of the cranberry. And what we've been able to do is develop a drone technology that can detect the disease, and we can detect it 2 to 3 years even before a satellite can detect it. And what this provides us is a way to detect the disease, to locate it spatially, and to create a recommendation to apply the protection or the fungicides that are needed to control the disease. One of the problems that we've run into is accuracy. As we've improved our resolution, so we can detect a very small area, maybe 1 meter or less of the disease developing. If the farmer can apply the fungicide to that spot, he can very efficiently control the disease. If he waits 2 to 3 years for a satellite image to show it, then it's going to be much harder to control the disease. The challenge is, how do you have a GPS unit that will get you to the accuracy to find that spot at a time when the disease is not apparent? It can't be seen. So this is one of the challenges that we've run into, but we've developed I've supported a company that is now using this technology to detect the disease, to provide very accurately geo-referenced imagery that can then be used by the farmer on his own GPS to make applications. And this is saving thousands of dollars, to the point where growers are spending up to $50 an acre for the product that they can then save money in the production. A second example, and one of the things that without slides, I forgot to mention, but in the process of collecting data from drones and then creating a product, there's a series of steps that we have to consider. For instance, what is the type of data that you want to collect? What is the frequency that you would collect it? How often would you collect this data? How would you process it? Would you process it automatically, or would you process it manually? So are there algorithms that you would use to simply create an output and not look at it any further, or would you try to process it manually? With the fairy ring, it's an example of where we process it manually. The next example is one where we would process it digitally. We simply allow the computer to create an orthomosaic. We collect many images over an area, create an orthomosaic, which is quite easy to do. Then we do a vegetative index, and we can start to immediately detect the presence of another disease, which is very difficult to control and requires manual pruning to go out and to see it. Ho, ho, ho. Where did that come from? Can we start the clock again? Look at that. So I'm going to go through these really quickly. Is it possible to have one extra minute? Oh, look at that. Okay, so this was one of the slides that I wanted to show. We're in a state now where we have digital technologies, but it's still important to have footprints in the field. You still need to be in the field and to use this. These are simply tools that make our footprints maybe a little bit deeper. And as I mentioned, we're going from more than just a toy. We're creating these kind of images using high-tech, very expensive types of drones. This is our data pipeline, which I was just describing, that we have data collection. We have to consider sensor type, frequency, classification, interpretation, delivery, implementation, and finally the effect. What is it worth? And if it's not worth anything, we're not going to be able to get anybody to use it. So this is the image that I had for the fairy ring disease that I was trying desperately to describe. Here's our UAV, or our drone orthomosaic projected over an Earth image. This is the fairy ring outlined in the image, so we're able to detect that. Here you can see it's nicely characterized from that drone imagery. Here's the recommendation that we send to the grower. And this is the result that we're able to detect these rings 3 to 4 years ahead of the satellite imagery, which makes it much easier to control and much easier to deal with. Second example, this is the detecting stem blight in blueberry. Here's an orthomosaic showing a blueberry field. And these examples can be applied to many, many different crops. It's also scalable to small acreage. If you classify it, all of a sudden, you can start to see small red dots showing up in your field. This is where the disease shows up. And now you can quantify and say that you have about 0.35% of the area, or 1% of the area, is diseased. By increasing the frequency of flights and collection, we can calculate how well we're doing at controlling this disease and removing it, which is the cultural practice. So again, this is something that growers are willing to pay for, and it's a useful tool to help them make money. Finally, the previous two technologies that I've discussed are ones that we use orthomosaics. The final one is one that's much more efficient, and it's where we use a stratified random sampling pattern. And what we want to do is estimate how much crop is present in this field. So we establish a grid over the field. We place one point in each grid, and then we create a map for our drone to fly to each of these locations. These maps come out with images that look like this. We know the size, very accurately the size, and we can start to do classifications on these. And we just got a grant to use deep learning to start to count the number of fruit in each image. So by having this data, we can now estimate the crop, we can estimate how much of the crop is exposed, and start to make management decisions based on estimating the crop. We can say, if we're being threatened for 30% of the crop, we can afford 15% of that loss to recover our potential losses. So we can make decisions based on the economics of the crop prior to harvesting. So that's my talk, just a few little bullet points for the opportunities. We have acreage mapping, very easy. These are things that we can do now, estimating losses, validating soils maps, disease identification, scouting, efficiency. One thing I didn't really mention at the beginning was the idea that we have agricultural scouts out there using, looking for problems, estimating problems, reporting back to the grower. By using this kind of technology, delivering digital data to scouts, we've turned them from simply scouts into power scouts. And that's our goal, is to create more, better tools to help people be guided to problems and detect these problems. So in development, creating meaningful vegetation maps. And when I say meaningful, I mean the ones that we can actually use on the ground in small farms. Creating yield maps, estimating yields, and then finally scouting and deep learning. So I apologize for the problem with the slides, and I thank you for your attention.